All right. Hello, everyone. My name is Anthony Iampietro, and my project for the summer, we'll actually be continuing the theme of exoplanets here from Dakota's talk, constructing a physically motivated model of activity-driven solar and stellar radial velocities. And I was working with Stephen Czar, Raphael Haywood, and Timothy Milbourne on this project. So a little bit of background on what our project was about. Dakota was talking about the transit method for detecting exoplanets. We are using something called the radial velocity method. And essentially what this is that we all know that planets orbit around stars because the star exerts a gravitational force on the planet. But this goes both ways. The planet also exerts a gravitational force on the star. And so as they rotate around each other in this sort of gravitational dance, due to the relative masses of a planet to a star, the planet has a very wide orbit, and the star just kind of wobbles in place. But we can still see this wobble as a Doppler shift. As the star wobbles towards us, the light is blue shifted. And as it wobbles away, it's red shifted. And because planet orbits shouldn't drastically change over time, that'd be a problem, we can track this shift back and forth over time and extract a radial velocity of the star. That's just the line of sight velocity of the star as it kind of wobbles back and forth. So to measure this, we use a combination of instruments. This one on the left here is a solar telescope. And what this does is it just points at the sun and sees the data, and then it feeds it into a spectrograph. This is the HARPS-N spectrograph. It stands for High Accuracy Radial Velocity Planet Searcher for the northern hemisphere. There is a HARPS in the southern hemisphere as well. And what this does is it takes in the data from the sun, feeds it into the spectrograph, and then it creates a spectra of the light from the sun. And it tracks this over time. It takes the measurements for the entire day. And then we can see those shifts as the star wobbles. The sun, is a star. It wobbles back and forth just like other stars. And we can track that shift over time in the spectra and look something kind of like this. So you can see the amplitude of these kind of variations in the radial velocity, it's delta RV, over about a period of 2 years for the sun, has an amplitude of about 4 meters per second on average. Now remember that we're looking for planets. So this data isn't just straight from the sun. This is corrected for the fact that we're in a solar system with 8 planets. Sorry, Pluto. And we're on one of them, and we're rotating, so you can get the idea that there is a lot of data reduction that goes into this point. But after doing all that, it doesn't just flatline at 0. We still have a lot of variation left over. And we'll get into what that is in a minute. Because first, we are going to just show some amplitudes of planets for kind of a context. So you see the sun sits at about 4 meters per second. Pegasi 51b is the largest and actually first exoplanet discovered back in 1995. It has an amplitude of about 56 meters per second. So that would be like this compared to that. Jupiter and Saturn in their current positions from the sun are about 3 meters per second. And Earth is the big question. As an exoplanet hunter, we're trying to find an Earth-like planet on a sun-like star in the habitable zone, just like Earth. So what's that signature like? Feel advanced. There we go. About 9 centimeters per second. Yeah, that's not a typo. It is that small, especially when compared to the leftover variations from the radial velocities of our sun. You would not be able to pull out that signal from these leftover variations. So the question is, remember, this is already reduced for all the corrections we need to make for the sun. So what is all this leftover variation? The answer is stellar activity. And on the next few slides, we're going through actually how we developed the model we work with. And as we go, we'll go into more detail about how the stellar activity can contribute to these variations. So a model for the variations is constructed as follows. And anytime you see RV, that's just the shortened radial velocity. We like our acronyms. So these model terms will be in plain text to represent the physical process that is the basis for them. And some of these terms will have like 2 processes in one. That's kind of just the way the derivation ended up working out. So this first term is sun/star spot rotation across a star. Now a star spot is just a sunspot on another star. They can have pretty different properties. Like sunspots are actually very tiny compared to some star spots, but they have the same general magnetic properties. And we're talking in the context of Doppler shifts. Remember, the star wobbles, red and blue shifts. Stars themselves, as you see, this hemisphere, or not hemisphere, this side is rotating towards you, and this side's rotating away. So the sun kind of has a background blue shift and red shift that, if there was no activity, would cancel itself out. But if you put something in the way of that, like a spot, that kind of creates an imbalance as it rotates across the disk and can create a variation in those measurements of the spectra. The second term is actually 2 physical things in one. In this terrifying image, this is a this is showing these little these cells here. They kind of look like popcorn. These are convective cells on the surface of the sun. And what these essentially are, it's just material on the surface of the sun flowing up to where we can see it and flowing out and kind of back down into these darker regions, these darker lanes between these. Now these individual cells are called granules, and the whole process is called granulation. And whether you have activity or not on the sun, these are always present. And remember, we're talking about Doppler shifts again. Anytime you have material flowing towards you, it's blue shifted. And there's a lot more area on these granules that's flowing towards you. So the sun has a natural net blue shift of light. And so if you put something like a terrifying sunspot on top of these, you block that, you actually block the convection that drives these cells, and you block the blue shift as well. And so we call this the suppression of convective blue shift. And this other term is horizontal flows around a sunspot. There's actually two of them. You can see one of them pretty evident here. This one that looks kind of like white specks flowing out from the sunspot, that's called the mote flow, and it's a little less than a kilometer per second. And this darker region just outside the heart, if you will, of the sunspot, is called the Evershed flow, and that's on the order of a few kilometers per second. And so you can imagine, again, we're talking about line of sight velocities. If you have these flows on the limb of the sun, you can have very large components of these velocities flowing towards or away from the observer. And we believe they may have some kind of effect on these variations. The third term deals with, again, the convective suppression of those granules, but for something called plage. Now, all plages is actually just a larger region of a smaller feature called faculae, and all these are just, they're little flux tubes that heat up the surrounding material and thus appear brighter. That's all these little white specks are in this image. And if you group them together, it's called plage. And this fourth term, we have the rotation of the plage regions across the disk, just like we have these spots rotating across the disk. And active regions have recently been discovered to have inflows, both directed from the poles and actually counter to the rotation of the star. Now, these are nowhere near as significant as the outflows from the sunspots. They're a few tens of meters per second, but they cover a much larger area, so they may still be significant. So we include them. So now we have our four terms for the model. These are all put into a linear combination to get our final model. But how do we actually go about applying it? We use measurable proxies, or we use measurable activity indicators as proxies for these effects. And we do this by selecting these proxies, which are just data we can measure from the sun, and based on which physical processes are best represented by these. So an important note, these are proxies. They are inherently imperfect, and some of these terms require a time derivative of these proxies. And so that can amplify these imperfections. So just keep that in mind. But just a little bit about each of these. Photometry is just the measure of light coming from a star. For the sun, this is a total solar irradiance. Filling factors is just the amounts of the visible sun, or about half of the sun, the stellar disk. It's just how much of that is taken up by the magnetic region. The unsigned magnetic flux is just a direct measure of how active the region is. It's because these are magnetically active regions. So we can measure that with something called the unsigned flux. That's just the familiar positive, negative polarity of a magnetic field. It's just the absolute value of that. So it's always flowing away from the star. And calcium-2 H&K line emission, Dakota talked a little bit about that. It's just the ratio of these two calcium-2 lines. One's called H and one's called K. They're very close together. And if you take the ratio of those, it's not as robust as magnetic flux, but it's still a pretty good indicator of magnetic activity, which is good because these are based on the sun. When we look to other stars, we lose those two. And we're stuck with photometry and calcium-2 line emission, which is all we need. We just need a light curve and some kind of magnetic indicator. And so we can use these two to actually run our model. And that is what we do. So actually running the model. We decided to run the model on two stars at the same time, our familiar home star, the sun. And we do this because it is the best spatially resolved star. And we can use that as a guide because we can see all the active features happening on the star, but we can integrate over the entire disk and bring it down to a point source, which is how we can, unfortunately, for now, only see other stars. And the other star we work with is Koros 7. This is about 500 light years away from Earth, and it is a host planet to two exoplanets. And it has one of the best data sets for those two, photometry and calcium-2 H&K. It's the most complete sets of those, and so we decided to run on that. And these are the data inputs for both of these stars. They're being shown simultaneously to show the similarity in the process. The x-axis is in time in days. This one's in time since the first day. This one's in Julian date, but it's still steps by day. And then the respective y-axes are the measures of photometry and the measures of the calcium-2 line emission. Now, the CORO 7 data is from 2012, when it was simultaneously observed by the CORO satellite and the HARPS spectrograph. And this period in the sun was just a month that we kind of randomly selected because it's about the same length as CORO 7. It features an active region, you can see here. And before we actually apply the model, we'll take a look at the radial velocity variations themselves. These are currently on the same y-axis scale of remember that delta RV comes back. These are the variations in the radial velocity. And remember that the sun is corrected for, the 8 planets in the solar system. But this CORO 7 data is not corrected for its planets yet. And CORO 7 is slightly more active than our sun. So you can see that the sun is greatly reduced compared to CORO 7. So just for visibility, we're going to zoom in on the y-axis for the sun. So keep in mind these are no longer the same scale, but you can see the variation better. So as I mentioned, for CORO 7, we have to actually include the planets because they're not reduced from the data. So we model them, and it comes out something like this. The 2 planets around CORO 7 are a rocky planet in a terrifyingly close 20-hour orbit, which what you see in this red one here, and a 3.7-day period planet. It's a super-Earth, mini-Neptune kind of for debate. And these planet solutions are from Haywood et al. 2014. We include these as a fixed term in our model. Remember, I mentioned that the model itself is a linear combination of those proxies. These are as a fixed term. In the future, we would like to actually have these parameters as a part of our model, allow them to vary, and so we can back out our own model for the planets. But due to time constraints, we're just using these because we can actually get a pretty good fit, as we see when we run the model. So we find that the model does a pretty good qualitative job of fitting the data, especially in periods like right here. You can see it does a really nice job as opposed to here. But that's going to be actually this happens for CORO 7 as well. You can see periods where it misses, periods where it does well, like right there. And so this is going to be one of our areas of future research is, well, what causes it to work well? What causes it to just completely miss? And we're just going to see where we go from there. Another way to actually look at these results is to look at the residuals. And all that is just the measured data minus the model. And here we see a pretty glaring problem, especially with CORO 7. The data has a periodicity to it of about 8.5 days. Now, in previous studies of CORO 7, they all get to this point as well. But they use something called a Gaussian process, which can essentially act as a signal like this to help absorb the noise, decorrelate the data, and can kind of get rid of the signal. But we're trying to model the physics behind these. And so we're stuck. But it's actually kind of a good sign that we're seeing this because we're catching up to these other studies that got to the same point. We just don't know where it's going to be, like I said, future analysis, figure out what the heck's causing that. And another problem is that if we overplot the measured radial velocity, remember, so these are no longer like the model. This is the residuals with the measured RV in the background. You can see the shape of the residuals kind of matches the measured RV. That's a sign that the data is still kind of correlated. There are some cases on the sun where we see something similar, like up here, but pretty decorrelated down here. So another area of future analysis as well, how to remove this correlation of the data, also while tackling the periodicity. And another way we can look at this is by something called an RMS, or root mean square. And we see that if we take the RMS of the measured radial velocities for both stars, and then we take the RMS of the residuals, we see that the number is significantly lower in both cases. And for an RMS, that's a good sign. That means that the model is doing something right. It is fitting to the data, even though we have the correlation problem and other factors. Something right is happening. And in an ideal world, this RMS of the residuals would be 0. That's impossible. That would be a perfect fit. And some processes on stars kind of prevent this from happening, aside from it just being kind of mathematically impossible. But, so yeah, that's a good sign, again, that something right is happening, and we are going to continue our analysis from there. So, just a quick summary. Modeling stellar activity is key to understanding and characterizing exoplanets. Remember back to that first graph where we had that tiny little orange line on top of the stellar variability for an Earth signature. We'd never be able to find that. So we have to tackle this problem to see these kinds of planets. We have determined measurable proxies for stellar activity that can be used to fit to these measurements of radial velocity. And most importantly, we have constructed a framework to include this activity. I mentioned that there's a lot more work to do on analyzing the performance of the models, decorrelating the data, but we have the framework to continue, and we see the first signs that it is working. So that is a very good sign for the future, and will drive our analysis as we go. And just some acknowledgments. We'd like to thank NSF and NASA for funding the program. Special thanks to Smithsonian, the TNG team, and HARP's in collaboration for the radial velocity data. And to my mentors, Steve, Raphael, and Tim, for all the help this summer. It's a lot of it. And to Kathy and Trey for hosting this REU, and again, just all of you for listening. Thank you.
Who's got questions?
Yeah.
What kind of star is Corona 7? Is it similar to the Sun?
Yes, it is similar to the Sun. Like I said, it's a little bit more active. I believe it's younger as well than the Sun, yeah.
Okay.
Is it?
Can you go back to your slide where you show all the different inputs to your model?
Yeah.
I like your videos, by
Oh,
the way.
thank you. This one?
Before that, it's probably
Oh, so this one.
4, 7, 8. Yeah, this one.
Oh.
So my question is, of those 4, what contributes the most?
That is an excellent question that I cannot answer yet. That is kind of the next big step in this project is we're going to see how, because remember these terms they're in a linear combination. And so after we run the model, each of these terms can be kind of backed out and we can see the relative power of, well, how well is, say, the Plage rotation affecting it? How well are these flows actually affecting it? And that's going to be, like I said, the next step of, well, how well are these individual models actually doing? And we've taken some preliminary looks, but we can't say anything conclusive yet to have results. That is on the agenda.
You said you're combining them linearly. I mean, it could be nonlinear if there's something that feedback on each other.
Mm-hmm.
That's
Interesting. Yeah.
Up in the balcony, there is a question.
Right. So for Conroe 7, you obviously have the ephemerides from the transits. But if you remove those and just fit your RV variations, what would you infer about the planets and how far off would you be from what your actual knowledge of the
So you mean like,
masses and theories of the planets having folded in with transit convention? Such an empty slot.
did we try something like that? I'm trying to think. I don't know, actually.
Well, that would have taken significantly longer than the time you had.
Yeah.
So we didn't really, as you mentioned, you included the terms fixed, and you're doing an least squares.
Yeah, this is a least squares fit to the measured RV.
You would have probably needed an MCMC to
Mhm.
do what James is suggesting.
But that could be an area to look into as we go beyond the summer, yeah.
That's going to be necessary
Mhm.
for the next step because, well, you need to fit everything in your model at the same time in order to optimize for all of the terms, right?
One more question? No? All right, let's thank Tony again.